Hello, everyone, and welcome to today's exciting webinar. This is our third webinar in 2021, and we have at least 12 more webinars planned for 2021. I'm Tim Stark and the host of today's exciting event. I'm a professor of civil engineering at the University of Illinois and the technical director of the Fabricated Geomembrane Institute. During today's webinar, we welcome questions and comments which can be typed into the questions box in the control panel. You may send in your questions at any time during the presentation, and we will address them at the end of today's presentation. The recording of this webinar, as well as a PDF of the slides, will be made available on the FGI website after today's presentation. PDH certificates will be sent automatically to all who attend the entire webinar later this afternoon. There will also be a follow-up survey after the webinar in which you can submit additional questions and make suggestions for future webinars. Okay, today our webinar speaker is Dr. Rudolph Bonaparte, who is board chairman at Geosyntec Consultants, Inc., headquartered in Atlanta, Georgia. He previously served as president and CEO of Geosyntec for 20 years, building the firm from a startup to 1,200 employees in more than 60 offices and 6 countries. He is also a professor of the practice in the School of Civil and Environmental Engineering at Georgia Tech in Atlanta. He is a member of the U.S. National Academy of Engineering, and today Rudy will present a presentation on design and performance of hazardous and low-level radioactive waste landfills, a 20-year case study. Rudy, thanks so much for squeezing this into your busy schedule, and the webinar is yours.
Great. Thank you, Tim. And thanks everyone for joining today. Tim described the title of the presentation, so I'll jump right in and say that the goal for today's webinar is to illustrate the design, construction, and performance of hazardous waste and low-level radioactive waste landfills. And I understand that this is a topic for at least some members of FGI, and that's how it came to be today. And we're going to use the U.S. Department of Energy on-site disposal facility, or OSDF, in Fernald, Ohio, as a case study. The OSDF is fully constructed, filled with waste, and closed. It was operated from November 1997 until October 2006, 9 years, with operational data available from January 2000 to the present, a period of a little more than 20 years. So we've got a nice record of facility performance. We'll review the OSDF regulatory requirements, conceptual and detailed design, pre-design studies, and construction. We'll also review operational data for the OSDF's leachate collection system, leakage detection system, and a horizontal well vadose zone monitoring system. We'll use that information to assess the performance of the facility after 20 years. This is an aerial photo of what was formerly known as the Fernald Feed Materials Plant in 1990 at the time of cessation of nuclear operations. The plant had operated for about 30 years. It had more than 150 buildings and a workforce of several thousand people. It was part of the U.S. Department of Energy's nuclear weapons complex, which included about 15 other facilities, including common names like Oak Ridge, Paducah, Portsmouth, Hanford, Savannah River, and others. As you might guess, with the name Feed Materials, Fernald was at the front end of the weapons process, feeding materials to other DOE facilities. Specifically, Fernald produced refined uranium, which is about 98% U-238, to be sent to other facilities, Oak Ridge and Portsmouth, for example, for isotope separation to concentrate the U-235, the fissile isotope of uranium. Fernald also made very high quality U-235 ingots that were then sent to other facilities such as Hanford for neutron bombardment to produce plutonium-239. So it was a feed materials plant at the front end of the process. When the plant ceased operations, it had contaminated soils, surface water, and groundwaters throughout its site. The U.S. Environmental Protection Agency added phenol to its Superfund list due to the widespread contamination. The name of the site was changed from Feed Materials Plant, or FFMP, to Fernald Environmental Management Project, FEMP, and then later to Fernald Closure Project, FCP. In 1991, DOE and the US EPA entered a consent decree requiring DOE to clean up the site. The contaminated media are listed here, and they included nuclear metals, process wastes, sludges, and contaminated groundwater. They also included, and of most interest to this lecture, about 3 million cubic yards of contaminated soil, building debris, equipment, and miscellaneous other materials. The materials I've highlighted in blue here. DOE retained Fluor Corporation as their program management contractor responsible for cleanup of the entire site. In turn, Fluor subcontracted to Geosyntec to design an on-site disposal facility that can take the contaminated soils and certain of the D&D wastes, including hazardous materials and low-level radioactive wastes. On behalf of Geosyntec, I served as the engineer of record for the original design. And let's take a quick look at that design now. The OSDF project is summarized here. Its contents consist mostly of low-level radioactive waste and solid waste containing RCRA hazardous materials generated during site remediation activities. And these included soils, ash, as I said, structural debris, building debris, road debris, asbestos, piping, wiring, and other materials. Pretty broad range of materials. The capacity of the facility needed to be 3 million in-place cubic yards. The operating schedule shown here, I already mentioned it, 1997 to 2006, 9 years. And its cost to construct, operate, and close the facility was about $224 million in 2005 dollars. Now, this doesn't include picking up the materials within the plant site, hauling them over, dumping them, and those kinds of things. It's just the physical operation in the cell. You can do the math, and this equates to about $76 per in-place cubic yard of waste. For this kind of an operation, a fairly cost-effective project. And in fact, we can compare it to the projected cost back in the day in 1995, 94, when these studies were first done, to the cost, the anticipated cost if this material needed to be shipped off-site to a low-level radioactive waste disposal facility in the Western US. And that estimated cost was about $1.5 billion. So you can see the cost differential here, the savings to the US taxpayers. Under the Superfund Act, which is officially named the Comprehensive Environmental Response, Compensation, and Liability Act, or CERCLA, the OSDF design needed to satisfy a variety of what CERCLA defines as applicable or relevant and appropriate requirements. Shorthand is ARARs, had to satisfy ARARs. Several of them are listed here, and I highlighted just a few. For example, one of the ARARs was EPA's criteria for hazardous waste landfills in 40 CFR 264. So we had to design to those requirements. Another is the Ohio EPA solid waste disposal regulations. We had to design to those requirements. Another is the DOE health and protection standards for uranium and thorium mill tailings in 40 CFR 192. That turned out to be very important. And then others that are listed here. So a wide variety of ARRs were put together to create the design criteria package that guided the design of the facility. And I mentioned the DOE health and protection standards for uranium and thorium mill tailings. Let's take a look at one of the specific requirements for that, because it was very important to this design. And it really led to one of the big challenges for the design, and that's to design a structure to last. So this ARAR 40 CFR 192 states that the controls, the environmental controls, in this case the OSDF, shall be designed to be effective for up to 1,000 years to the extent reasonably achievable, and in any case for at least 200 years. That's a very long design life for really any kind of engineering structure, and certainly for a waste containment facility. And how does one go about designing that? And how does one even really think about how long that is? I find it helpful to think about it in historical terms. So for example, what was going on in the world 200 years ago? And if you think about it, that was about the time of the famous Lewis and Clark expedition to find the Northwest Passage through the North American continent, starting in St. Louis, Missouri, and ending on the Pacific coast of Oregon. That's a long time ago. We think about 1,000 years ago, that was about the time that Leif Erikson and the Vikings first landed in Newfoundland in eastern Canada and stepped foot on the North American continent. And so if you think about the Vikings, that's certainly in the antiquities of history, a very long time ago. That's what we're designing for. And even Christopher Columbus, that's roughly 500 years ago. So this gives you a sense of the time frame of the design life. So how did we think about it? How did we approach it? And our approach was to develop and specify materials, design features, and maintenance procedures to mitigate what we'll call potential pathways for performance degradation over the OSDF design life. So you build this thing, it's working perfectly on day one, but it's like anything, it's going to have a potential to degrade over time. So we needed to think about how to address these degradation pathways. And at a high level, we focused on 6 listed here. Internal hydrologic degradation, i.e. failure of the leachate collection system or leakage detection system. External hydrologic degradation, e.g. Liner system degradation such that perched groundwater at the site would migrate into the liner material or the waste materials. Or degradation of the final cover system, so precipitation infiltrated through the top. Geotechnical and seismic instability, facility flooding and soil erosion, biointrusion by plants and animals, and uncontrolled ecological succession. So we thought about things in these buckets, and we also thought about it holistically. And as I said on the previous slide, we looked at ways to select materials and engineered components and redundancies and maintainabilities that would allow us to mitigate the potential for these things. So for example, in terms of selecting materials and geometry to maximize design life of the engineered components, as an example, we utilize thick quartz-based, silicate-based mineral granular layers, not carbonate-based layers, nor geosynthetics for the LCS and LDS drainage layers. As another example, we use thick geomembranes because we know they degrade primarily by surface mechanisms, which in addition had very stringent, probably the most stringent specifications at the time of construction for environmental stress, crack resistance, and other properties. As another example involving geometry, we used relatively flat final cover system slopes. The maximum slope was 6 horizontal to 1 vertical to limit soil erosion. Redundancies, the entire OSDF is underlain by a double composite liner system. So 2 complete liner systems stacked on top of each other, with the lower composite liner having 3 complementary components. A geomembrane, underlain by a GCL, a geosynthetic clay liner, underlain by a compacted clay liner. As another example, the leachate collection system pipes. We had a primary pipe coming out of each cell to a valve and pump house, but we also installed the secondary pipe. Both of those are completely maintainable, and we used well, going on to maintainability, we used very thick wall pipes to, again, maximize design life. Straight runs only with clean asset, we could clean out the entire length of the pipe over, its essentially entire design life. As another example of maintainability, we designed the facility primarily as an above grade facility. This was to allow us to access as much as possible the leachate collection and leakage detection systems, which is harder to do in a buried facility. And so above ground was good, we thought, in this case. As another example, the cover system is designed as a relatively flat slope passive element that can be designed for as long as is determined necessary by future generations. And lastly, I'll mention that ultimately the federal government is responsible for the maintenance and security of the on-site disposal facility in perpetuity. Going on with the design, it included a lot of analyses and calculations that are listed here. This was done back in 1995, where you submitted your engineering packages in hard copies to your client. So the calculation packages here were 4 4-inch thick binders of calculations, double-sided, and they included all of the elements that are shown here. I've highlighted the main categories of calculations, but you can see that for many of the main categories in yellow, there's 5 or 10 subcategories of calculations in each main category. So all told, I've never added them up, but there's probably 70 or 80 different sets of analyses for this design. But the main categories are OSDF layout, geotechnical involving static slope stability, seismic slope stability and deformations, liquefaction potential, seismic hazard analysis, and all those kinds of things. Settlement is another geotechnical area. A whole set of analyses related to the liner system, including uplift, tensile stresses, cushion layers, and a variety of things. Under leachate management, leachate generation, leachate collection system design, leakage detection system design, leachate transmission system design, final cover system design, a lot of categories of things there. Surface water management during the OSDF operation, enclosure, and then surface water management in the post-closure period. Support facilities, power, potable water, sanitary, and other things, borrow area, impacted materials management, vadose zone monitoring, groundwater monitoring, and roads, intersections, and overpasses. So that gives you a sense of the range of analyses that were conducted for the facility. Here's a list of the 60 E-size design plan sheets developed for the main regulatory submittal package, first to DOE and then to EPA and Ohio EPA. And for each of those agencies, it involved review and approval. And you can see that the drawings are categorized as general drawings, civil, which is most of the set, electrical, mechanical, and structural. And so after these were approved by everyone that needed to approve them, we prepared certified for construction packages. That's DOE terminology for each phase of construction. So for each cell, there was a certified for construction package that went to the contractor. That's what they built off of. And after construction and after CQA was complete, a record drawing or an as-built drawing was prepared for each cell. And we did that as well for the leachate transmission system. So there, you can imagine, in addition to this master set of drawings, there were probably 20 additional sets that were produced during the 9 years of the active operation of the facility. So these tend to be pretty substantial efforts over a long period of time. Here's the master specification list: site work, concrete, special construction, mechanical, electrical, structural, metals. There were a few other things I didn't add. And these are in the 1995 CSI format, not current CSI format. This slide shows the OSDF footprint overlain on an aerial photo of the phenol plant. You can see the plant production area to the west, to the lower part of the photo, and the OSDF in an open field in the middle, the upper part of the photo, which is to the east. I've highlighted that the footprint of the landfill down to the toe of cover system slope, so the entire footprint is about 80 acres, with the line footprint that received waste being about 60 acres. I think that's about it. You can see the plant production area in the lower portion of the slide. Here we see, I'm going to try to turn on my laser. Oh. Yeah, here we go. Here is a north-south section through the OSDF at 10 times vertical exaggeration. And we drew it like this to make it easy to see everything. You can see cell 1 to the north, that was constructed first, and cell 8 to the south, that was constructed last. You can also see that the site overlies a high-value primary drinking water source, the Great Miami Aquifer. Now, normally, CERCLA ARARs prohibit one from building a hazardous or low-level radioactive waste disposal facility over a high-quality aquifer. To site the OSDF at this location, we needed to obtain an ARAR waiver from EPA and Ohio EPA. In other words, they needed to waive that requirement that we couldn't put a facility at this site. One of the reasons that the ARAR waiver was granted is that our design left in place a minimum of 12 feet of very low permeability gray till and brown till. So we had protection for the aquifer that included not only the liner system and other features I'll show in a few minutes, but the in situ clay till layer that in most places was quite a bit more than 12 feet, and that one location was as little as 12 feet. So I already noted that this was designed primarily as an above ground facility for two reasons. One is to preserve the till layer, and the other I mentioned earlier, to maximize maintainability of the facility. Here's an east-west cross section, east to the right, west to the left. The top cross section is at true scale, and you can see the relatively flat final cover system slopes at 6 horizontal to 1 vertical. And in the lower cross section, we've drawn it at 3x vertical exaggeration to show just a little more clearly a few things. You can see the natural slope of the ground and the gravity drainage from east to west. You can see how the LCS and LDS pipes discharge into leachate collection valve house. That's where the leachate transmission system carried leachate and other liquids about a half a mile through double wall pipes through a wastewater treatment system that was on site. And so you see the layout here. Here is the double composite liner system that underlies the entire facility that I mentioned a few moments ago. We have an entire primary liner system and then essentially an independent secondary liner system, so double composite liner. The primary liner system starts, I'll go from the bottom up, a primary geosynthetic clay liner, primary geomembrane liner, geotextile cushion layer, leachate collection system, which is a 12-inch thick layer of gravel, quartz silicate gravel, geotextile filter layer, a protective soil layer, and then the first layer of waste, which we call special impacted material. This needed to be soil waste. We did not allow any structural debris within this zone, only soil-like waste to protect the liner system. So this primary liner is meant to entirely contain leachate and allow it to flow out through the leachate collection system pipes. But as a redundant measure and to meet the ARRs, we have a secondary composite liner system that starts with a leakage detection system, again, another 12-inch thick layer of granular material, highly permeable, a geotextile cushion layer, secondary geomembrane liner, secondary geosynthetic clay liner, and a 3-foot thick compacted clay liner with a hydraulic conductivity of 1 × 10⁻⁷ centimeters per second or less. All of this sloped at 2% towards the low point in each landfill cell. So if the liner system underlies the waste, the final cover system overlies it, and the final cover system, if we include this contouring layer, is 9.75 feet thick, but almost from the ground up to the height of a basketball hoop. Beneath the cover system, we finished filling each cell with a 3-foot thickness of special compacted waste, select waste, that again was soil-like material and could not include any structural debris. So above the contouring layer, we had a 2-foot thick layer of compacted clay cap that also needed to have a hydraulic conductivity not more than 1 × 10⁻⁷ centimeters per second, a geosynthetic clay liner, a geomembrane cap, a geotextile cushion layer, a 1-foot thick layer of cover drainage material, a 3-foot thick bio-intrusion barrier layer, the upper lift of which we vibratorily compacted into it a chokestone layer, so we had compatibility with the overlying granular filter, transition zone, and then a 21-inch thick vegetative soil layer and a 6-inch topsoil layer. The design goals for the cover system were to limit to the extent reasonably achievable, going back to that LLRW principle I mentioned at the beginning of the presentation. So to limit infiltration of precipitation, animal and root intrusion, surface runoff and wind-driven sheet erosion, formation of gullies by surface runoff. We don't normally consider gully initiation in the design of municipal waste landfills, for example, but I learned a whole lot about it way back in the day when we were designing this, and we designed for that. The release of radon-222 to the atmosphere and human and ecological contact with waste. There were a variety of special pre-design studies that we conducted for the project, and I'm going to talk just very briefly about 3. One was to demonstrate that CCLs could be constructed using on-site soils to achieve a low permeability of 1 × 10⁻⁷ centimeters per second or less. The second was to demonstrate compatibility of HDPE geomembrane liner material with radiological and hazardous waste leachate. And the third was to measure geosynthetic soil interface strains and GCL internal shear strains for use in geotechnical slope stability analyses. I have 1 slide on each of these programs. The first special study involved constructing large test pads using the same soil processing, placement, and compaction procedures required by the technical specifications, and then testing the constructed liner in the field and lab. You see in this first photo, compaction of the test pad soil with a CAT 815 pad foot compactor. Here we see a schematic of a sealed double ring infiltrometer that was used to obtain large-scale field measurements of CCL hydraulic conductivity. You see the 12-foot by 12-foot outer ring and outer pond of water that's infiltrating, but then you see a sealed 5 by 5 inner ring connected to a flexible bag. So that is entirely self-contained. And if you think about one-dimensional vertical percolation, we can measure the loss of liquid in the bag as the amount of water that's infiltrating within the 5 by 5 inner ring. In this photo, we see the installed sealed double ring infiltrometer. The instruments you see around the 4 sides of it are tensiometers that are used to measure the wetting front advance. In fact, you can see it in the previous schematic. We need to know the distance of advancement of the wetting front for the calculation of hydraulic conductivity. And here are the 2 of the SDRI test results. we see, we've reported here the dry density of each sample. They're about 107 PCF, and the moisture contents about a little over 19%. So these are, probably, I don't recall off the top of my head, at 98% of standard Proctor compaction on the wet side of optimums, at a degree of saturation on the order of about 90%. And you can see that the resulting hydraulic conductivities from the SDRIs were a little over 1 × 10⁻⁸ centimeters per second. So very, very good results, very low permeability, nice material to work with, although we did a lot of screening to get rocks out, and then we used a big Caterpillar soil processor to break down clods. So it was a fair bit of work. But once you did all that, it was a nice material. And here are 2 lab results from Shelby tube samples that we obtained from the test pads and tested in flexible wall permeometers using AST method D5084. And you can see they're about at the same dry densities and the same moisture contents, and we got roughly the same hydraulic conductivities. So this was really very helpful, because it told us Ohio EPA had a concern whether we could use Shelby tubes to obtain hydraulic conductivity results that they were comfortable were indicative of the in situ liner system. And these results gave them the confidence to allow us to use Shelby tube samples as a construction quality assurance test, and not have to do something larger scale like taking block samples or something like that, which would have been really difficult. The second special study involved using the EPA 9090 chemical compatibility testing methodology to evaluate whether radiological and hazardous waste leachate adversely affected the HDPE geomembrane liners that were considered for the design. And we tested all of the major manufacturers' geomembrane liners as part of this study. The tests were intentionally conducted using a synthetic leachate with radionuclide activity more than 3 orders of magnitude higher than the actual measured activity of leachate anticipated and ultimately generated by the OSDF. And that was so as to provide a radiological dose during the tests roughly equivalent to an OSDF 250-year design life. If you go in and study the physics of the effects of radiation on polymers, it's the dosing that has the biggest effect, and the energy that you're imparting to the material that has the biggest effect on or potential effect, I should say, on those. So we focused on dosing. And then also other constituents for the hazardous components, but I'm not going to talk about that today, things like VOCs and other chemicals. In the tests, I think as most of you know, geomembrane samples are immersed in leachate baths of 23 and 50 degrees Celsius for up to 120 days. And then they're tested, they go through a testing regimen to see if effects can be discerned. And the results of our tests, we didn't find any effects. We didn't measure anything that it was indicated an onset of degradation was occurring. We didn't see a loss in environmental stress crack resistance. We didn't see surface degradation mechanisms. We didn't see a change in OIT. So that was a good result. And in fact, after doing this testing and looking at subsequent testing done by others at Oak Ridge and other facilities, I was invited in 2016 to give a talk at the ASCE Geo Institute conference honoring the career of Bob Kerner, which I was obviously very, very happy to participate in. And I talked about the subject of geomembrane leachate compatibility for U.S. Department of Energy CERCLA waste disposal facilities, and putting together all the work that had been done, the work we had done at Fernald, some work that we were doing at the time. We're currently working at Portsmouth on a similar facility, and work we had done at Portsmouth and work that had been done at others, work that had been done by Craig Benson and his students. The conclusion that we reached is that the service life for HDPE geomembrane liners in these facilities should be well in excess of the 200-year minimum facility performance period of 40 CFR 192 and DOE Order 458.1, may approach the DOE performance period goal of 1,000 years. And in fact, a very simple takeaway is temperature for HDPE is a significantly larger concern than these radionuclides. So, we have an interest in heat generation in MSW landfills. That's not an issue here. These are buried, tends to be pretty cold in the ground, and we don't see the level of thermal reaction that one might see at an elevated temperature facility. The final special study I'll mention is direct shear testing of liner and cover system interface strengths and GCL internal shear strengths in accordance with AS2 procedure D5321. For each OSDF stability condition, including both peak and large displacement conditions, we first establish shear strength envelopes, one shown here in red, and indicating the shear strengths required to achieve target slope stability factors of safety. So on the strength plot, for the strength condition we're considering here, strengths need to be above the red line. We then tested commercially available products to make sure that the measured strengths shown in the plot as open and shaded circles and squares exceeded the required values represented by the red line. We see here that for the tested geomembrane GCL interface, the measured interface strengths are higher than those required to achieve the target factor of safety. That's a good thing. These results told us that we could use the red failure envelope in our specifications and require the contractor to provide products with interface strengths and internal strengths that fall above the various red lines for the various stability conditions. And doing so with confidence that such products were commercially available based on the test results, and the contractor wouldn't come back with a change order request because he couldn't find a material to meet our strength requirements. Moving on, let's now take a very quick look at OSDF construction, filling, and closure. Just a few photographs. We see in the left-hand photo the surveying of cell grades, and in the right-hand photo, installation of the secondary geosynthetic clay liner over the secondary compacted clay liner. In the left photo, we see extrusion seaming of an HDPE geomembrane at a patch location, while in the right-hand photo, we see the geomembrane installer conducting an electrical leak location survey. The left photo is showing placement of the leachate collection layer drainage gravel onto a 3-foot thick unloading pad. We wouldn't let that big truck go right on the geosynthetics or even on a foot of granular material. It had to stay on these unloading pads. And then on the right, we used low ground pressure dozers to push the material out and spread it around the cell. Here we see on the right demolition of structures at Fernald ongoing. The structural steel, concrete, piping, wiring, and other building contents, tank contents, other things were size reduced. Pipes, large pipes were cut, structural steel was cut, concrete was, I wouldn't say rubblized, but it was reduced in size. And then taken over and placed in the OSDF cells and surrounded with compacted soil, which we see in the two photos on the right-hand side. This was a highly planned out process to minimize the potential for post-closure total and differential settlement and for raveling of soils within the OSDF into voids. If you could imagine having a pile of structural steel debris, the potential for raveling from above. So to avoid those kinds of things. All incoming waste was manifested, had to meet strict waste acceptance criteria, and had to be placed in strict accordance with the approved waste placement plan. These photos show steps in construction and testing of the compacted clay component of the final cover system. In fact, on the way on the right-hand side, you can see the soil stabilizer, the soil processor I talked about for breaking down clods in the material, and on the lower left, a smooth drum roller that, after you went through all the kneading compaction with the pad foot compactor, the Caterpillar 815, we'd smooth roll the surface prior to placing the geosynthetic clay liner. On the left, we see from the right side, so the right side of the left photo, the tan material is the compacted clay cap. The light gray material is the geosynthetic clay cap. The thin strip of a little bit shiny black material is the geomembrane cap, and then we see the geotextile cushion layer. And then on the right-hand photo, we see the low ground pressure dozer spreading the covered drainage layer material. On the left, we see placement of the biointrusion barrier layer. And on the photo on the right is really pretty interesting. So if you can look carefully, we obviously see on the left-hand side the compacted clay cap. We see the smooth drum roller rolling it out. And then we see the light material, the geosynthetic clay cap. We then see mostly the black material is the geotextile cushion, but you can see just little fringes of the geomembrane cap on the left side of the geotextile. Then the granular covered drainage layer and the biointrusion barrier layer. And the gray material on top of the biointrusion barrier layer is actually the chokestone layer I mentioned earlier. Then the granular filter layer, coarse sand material, and cover soil layer and topsoil layer. So if you start at the top of the compacted clay cap, the top of the compacted clay cap, all of the cap materials above it, or the cover system materials above it, measure 6.75 feet in thickness. In this photo, we get a good sense of the sequence of OSDF construction. The first cell that was constructed is cell 1. You can see here that at the time of this photo, it is filled and closed with vegetation established. Then you see cell 2 to the immediate south of cell 1 with vegetation on cell 2 just becoming established. And then to the south of cell 2, you see cell 3, which is filled and just starting the closure process. And to the south of cell 3, cells 4 and 5 are active and being filled at that time. And then finally, cells 6 and 7 are under construction. So you get a sense of how we marched from north to south across the site to develop, fill, and close this facility. And then finally, if you look to the upper right, you can see the plant site and the progress that Fluor and their team have made by this point in the cleanup and D&D of the plant. And here's an aerial photo with OSDF closure complete in October 2006, with cell 1 to the north at the top of the photo and cell 8 to the south at the bottom of the photo. If you look carefully, you can just make out the 8 leachate valve houses on the west side, on the left side of the facility. And if you look to the lower right-hand corner of the photo, you see the Great Miami River that's connected to the aquifer underneath the site. So we'll finish up today's webinar in just a few more minutes. Look at performance results for the OSDF. As I mentioned earlier, we now have nearly 20 years of monitoring data. And this is just meant to remind you that what we're going to be looking at. We're going to be looking at flows and chemical quality data for liquid coming out of the leachate collection system pipe and out of the leakage detection system pipe. And we'll also be looking at just a little bit of information about collected liquid from the Vadosome monitoring system, or VZMS, below the facility. There's lots of data. We could spend lots of time on this. I've just cherry-picked a few things to highlight several messages. This figure shows leachate flows from the OSDF measured in gallons per acre per day. You can see that on the vertical axis, gallons per acre per day, or GPAD, versus time from 2000 through 2019. You can see that the maximum leachate flows occurred when the cells were open, and we see the periods in which all the cells were open. And that peak flows, not average flows, but peak flows were on the order of 2,000 to 3,000 gallons per minute per day during much of the operating period of the facility, and then reducing as one moves towards the closure period. Now, these flow rates are higher than we predicted during design using the EPA hydrologic evaluation of landfill performance model, or HELP model. And those predictions, and these are averages, so we should probably compare these to something that's an average in this range here. But these are the predictions we made during design, and you can see they're lower. They're certainly lower than the peaks. They're even lower than, and I should probably do this, is average these out and see what the averages are, but they're probably somewhere in here. And in evaluating this, we believe there's two reasons for the lower leachate generation rates. One is that cells stayed open longer than we had predicted or we had estimated during the design. So if you have more open cells, you're going to have more leachate generation. And two, and I think this is fairly important, in design, we did not include the very large amount of water that was used for dust suppression on the working face almost continuously throughout the entire period of OSDF filling. Now, they may have been spraying something like 50 to 100 gallons per minute from several industrial hoses during much of the operation of the facility. So we think those are the two main reasons for the higher leachate generation flow rates. And you can see that at the time of facility closure or shortly thereafter in 2006, leachate generation within the facility reduced to very, very low rates, which is a good thing and something we would anticipate. This figure shows the monthly average LDS flow rates, an LDS, let me emphasize, leakage detection system for the OSDF cells from 2000 through 2019. And this plot actually shows the individual cells. The data shows that the peak monthly flow rates ranged from a few gallons per acre per day to 14 gallons per acre per day, more than 2 orders of magnitude lower than the monthly average leachate collection system flow rates shown on the previous slide. This is a good thing. We're seeing much, much, much less liquid in the leakage detection system than the leachate collection system. The leakage detection system peak flows occur during the active operation of each cell, and as you can see, they drop off quickly as each cell is filled and closed. Comparison of the chemical quality of the leachate collection system flow to the leakage detection system flows shows that most of the LDS liquid is not primarily leachate resulting from leakage through the top liner, but rather water from other sources. This slide takes the monthly LDS flow rates by cell and plots them versus a lapsed month since the cover system was put on a cell. So we tried to normalize these results a bit. You can see how for all but one cell, flow rates had dropped to almost zero within 24 months of closure, and it took about twice that long for one cell for that to occur. But what this is telling us is that basically the leakage detection systems for the cells are all but dry, which is a good thing and provides assurance that the OSDF is not leaking leachate into the environment. Last slide before my conclusion slide. So as I already said, not only is there almost no flow coming from the leakage detection system, but as I mentioned a moment ago, the flow is primarily not leachate. This conclusion is based on the different chemical fingerprints for flows from the leachate collection system and the leakage detection system. This slide highlights results for just one parameter, total uranium. For each of the 8 OSDF cells, we can see their uranium concentrations in the LCS, the uranium concentrations in the LDS, and the uranium concentrations in water collected in perched water from the Vadosone monitoring system. And there is some contamination in the Vadosone monitoring system, but fate and transport analyses and risk assessments demonstrated that it's low enough not to be of consequences. So it was left in place below the OSDF, and it's not migrating at any level of concern down to the Great Miami Aquifer. And in fact, because of other contamination, there's a very large pump and treat system working to clean up the Great Miami Aquifer. Let me draw your attention to this last column. It shows the ratio of LDS leakage detection system concentration to leachate collection system concentration. And we can see that the range of ratios is on the order of 10 to 20%, meaning that the uranium concentrations in the LDS flows are 5 to 10 times lower than in the LCS flows, and are in fact closer to the concentrations in the Vadosone monitoring system. So we think these are coming primarily from construction-related activities, consolidation water, although we don't have a direct route for that consolidation water. But the flow volumes themselves are so de minimis that they're kind of meaningless numbers at this point in time. So to conclude, the OSDF is the engineered environmental legacy of a major Cold War nuclear production facility. When constructed, it was the most technologically advanced, low-level radioactive waste, hazardous waste disposal facility in the US. It's the first such facility to systematically address a 200-year-plus service life through the use of geosynthetics. Facility performance after 20-plus years post-closure, at least post-closure for the first cells, is in accordance with design expectations. LCS flows have dropped to very low levels. LDS flows are near zero. LDS flows are primarily not leachate. And while I didn't talk about it today, we've looked carefully at the performance of the final cover system. The final cover system is performing well, requiring only limited maintenance and repair. So today, the phenomenon
See, Rudy, did we lose you? Let's hope Rudy comes back here in a minute. These are his last two slides. Okay, I'm going to cover my last three slides while Rudy hopefully comes back on. Oh, see, is Rudy back? The last three slides that Rudy has at the end of his slide deck are the first slide is contact information for Rudy, me, and Jen Miller if you'd like to send additional questions. The next slide is our next FGI webinar, which is titled Static and Seismic Veneer Stability Calculations. And that's on Tuesday, April 13th, 2021 at 11 a.m. Central Time. And Dr. Nevin Matasevich of Geologic Associates will be giving the webinar. Finally, the FGI website has all of the prior webinars stored there. You can access the webinars, and if you have not watched them previously, obtain a PDH certificate for 1 hour if you watch the entire webinar. As well as the webinars, there are podcasts, video podcasts, quizzes. I've put some quizzes up there on engineering and geosynthetic type issues, and technical papers, calculators for pond leakage, panel weights, installation costs, a photo gallery if you'd like some photos, and our section on women in geosynthetics for the profession. So let's see if Rudy is back. Rudy, can you hear me? Okay, well, we have about 20 questions submitted. Thank you very much. Looks like I will set up a podcast with Rudy to answer these questions. And I will post that on the website as well. Let's see. There's a chat. Okay. Let's see. Rudy, are you back now? Let's see. No. Okay, so everybody, thanks for attending. Looks like Rudy's lost his internet connection. So I will set up this podcast with Rudy and answer these 20 or so questions. Thanks so much for attending the webinar today. Again, our next webinar is with Dr. Nevin Matasevich on the static and seismic stability of final cover or veneer cover stability calculations, how to perform them. So it's be really like a design type webinar. Okay. Let's just check one more time. Yep. All right. I still don't see Rudy. So everybody, hey, thanks so much for joining. And I will get these questions answered in a podcast. I hope I will see you next month, April, to talk about the static and seismic stability of final cover systems with Nevin Matasevich on April 13th. Thanks for attending.